You are watching Darasa Online.
Welcome students to Darasa Online. I'm Cyprian Mgina, a physics teacher. And today we are going to study, we are going to look onto the topic of current electricity to the subtopic of an alternating current, the AC theory. And this is the first part, where we shall just be able to go and look into on how we can be onto the measurement and the analysis of the AC through circuit elements. And we shall be looking basically the three circuit elements: a resistor, a capacitor, and an inductor. But to start with, we really need to know the applications of an alternating current. There is a difference between an alternating current and a direct current. An alternating current is a current which is really oscillating, pulsating from the positive maximum to the negative maximum. And this alternating current have several uses in domestically, in industries, at home, where we are really using an alternating current. Why is it so much popular as compared to a direct current? An alternating current is so much popular because it can be easily converted from one voltage to another voltage. For example, if it's being used, let's say, into an electrical system like radio, TV, or whatever, there are several devices within an electrical system or within such kind of a radio or a TV, of which some particular parts might need a current of a certain voltage. So to convert a current from a certain voltage to another voltage is really possible if that particular current is AC. So AC is much popular because you can just be able to play with by changing its voltage from one form to another. That's one advantage of using an alternating current. And another advantage of using an alternating current is that an alternating current can be transported very easily from one location to another. For example, we need to transport, let's say, an electrical power from Kilombero to Dar es Salaam or from Kilombero to Bukoba. So it is very possible to transport such kind of an electrical power whenever it is at a very big voltage. A very big voltage. So it can be transported easily with a minimum power loss. There are several other advantages of the alternating current as compared to the DC. But there are also some disadvantages for an alternating current. You could just be able to find that an alternating current have got an attracting behavior. Whenever one gets a shock, an AC really it attracts to somebody who has got a shock as compared to a DC, which have a repelling behavior. That's one. And also an AC cannot be used, let's say, in electrolysis or in electroplating. That's where it's only DC can just be used. These are just a few disadvantages for an AC. But still, this particular current, whenever it passes through this particular three circuit elements, which are just going to look like a resistor, an inductor, or a capacitor, it have got some effect. It have got some effect of which we shall just be able to see as we are really going to look onto the other coming parts. The effective value we are talking about for that particular alternating current, whenever it's passing through a resistor or a capacitor or an inductor, have got a particular value which could produce a certain final effect, just like whenever we are having a direct current crossing through these particular devices. And this, because it's a revision, we are not just going to derive that particular effective current or the effective current which will just be found. The effective current which will just be found actually will just be equal to 0.707 of the actual current which will just be flowing. So the same thing can just be obtained even for the EMF. First of all, we need just to see whenever we are having a current made to pass through a resistor. Whenever an alternating current is made to pass through a resistor, we won't be able to go to the first principle, but I'll just be able to mention it to you because I believe you have already done this in a class. That the current, whenever is made to pass through a resistor, the voltage, the alternating current through a resistor, and the voltage, they are always in phase. So we are having our symbol for a resistor like that, and in this case, we are saying that the voltage through a resistor, okay, and the current, they are in phase. They are in phase in a resistor. They are in phase in the resistor. It means that they are all moving. It means that whenever they are passing through it, if an alternating current goes like this, also the alternating voltage will be going like this. They are all moving. They are all moving in this way, that they are in phase. Whenever I'm talking about the voltage or talk about the current I through a resistor. This is the first part. If we're just going to look, let's say, for an alternating current through a capacitor. If we're just going to look an alternating current through a capacitor, we just found that the voltage through a capacitor lags behind the voltage through lags behind the current by 90 degrees. That is by a quarter of a cycle. So here we are saying that the voltage through a capacitor, the voltage through a capacitor lags behind the current by a quarter of a cycle, or by 90 degrees, or by pi over 2, okay, or what we call a quarter of a cycle. A quarter of a cycle, okay? We all know that whenever it's moving like this, from this to that point, this is one cycle. So it will just be lagging behind. The voltage through the capacitor lags behind a current by a quarter of a cycle, that is pi over 2. But whenever I'm just going to look for an alternating current through an inductor, whenever we're just going to look for an alternating current through an inductor, we just found that that particular voltage through an inductor leads the current by pi over 2. So the voltage through an inductor leads the current by pi over 2, or by what we call 90 degrees. Okay, or what we call, it leads by a quarter of a cycle. It leads by a quarter of a cycle. This is the actual behavior, and this should have to be in your mind all the time whenever you are embarking onto solving onto some particular problems. Let us now just try to look. We are saying that the actual circuit elements we are having here is the resistor, a capacitor, and an inductor, whereby these three circuit elements can just be arranged whether in series or in parallel. But today we shall just be able to look the arrangement of this particular, we shall be able to look whenever these particular circuit elements are just arranged in series. But before going and look that kind of an arrangement, we really needed to see the behavior of this particular current whenever it's made to pass it through these particular three circuit elements. That first of all, whenever a current is passing through a resistor, there is a power which will be dissipated through it. and that particular oppositional force which is being shown by a resistor, a pure resistor, that is what we call the resistance, and this is measured in ohms. So to a resistor here, we are having the resistance, an oppositional force provided by a resistor to an alternating current made to flow through it, be called it's an opposition, what we call it, a resistance measured in ohms. But specifically for a capacitor or for an inductor, such kind of a resistance, such kind of an oppositional force provided by a capacitor or an inductor, whenever an alternating current is made to cross through it, we are not calling it a resistance. We are just calling it a reactance. And for that case, we are having what we call capacitive reactance and inductive reactance. Now, let us just look very quickly upon these two kind of the behavior. For a resistor, it's very easy because we had just been dealing with a resistance even in O level. But here comes what we call reactance, which is obtained in an inductor or in a capacitor. This is what we call reactance. This is what we call reactance. So we are talking about the reactance in inductor or in a capacitor. So let's just look reactance in inductor. Reactance in inductor. Reactance in inductor, we are calling this to be X sub L. Okay, this is the reactance in the inductor, and you'll be able to find that whenever I'm talking about, let's say the voltage through an inductor will just be equal to the current I times inductive reactance. So we're going to get the voltage through an inductor. And actually, from the first principle, you need even not to derive this. From the first principle, we'll be able to find that the inductive reactance, this is just be equal to omega times L, or just the same as 2 pi f for the omega, which is equal to 2 pi times the frequency times L. This is what we call an inductive reactance. This is what we call an inductive reactance, the XL. This is what we call an inductive reactance. But for a capacitor, we are having what we call reactance in capacitor. For a capacitor, we are having what we call X sub C. This is what we call capacitive reactance. And the voltage through a capacitor, this is just equal to the current times the capacitive reactance. And from the very first principle, the derivation to obtain the capacitive reactance, this is just equal to 1 over omega C, or simply as 1 over 2 pi f times C. So this is what we call the capacitive reactance. This is what we call the capacitive reactance. Okay, students, now I need now to take you to such kind of a circuits having a resistor, an inductor, and a capacitor connected in a series. So we shall be able to discuss 3 cases only at this part. And in these 3 cases, first of all, we are going to start by looking whenever we are having a resistor and a capacitor connected in series. And we shall look at the second case whenever we are having a resistor and an inductor connected in series. And our last case, we shall be able to look whenever all 3, a resistor, a capacitor, and an inductor, they are connected in series. So Whenever they are connected in series, we could just be able to see that the total opposition force of the combination, of which now we are not calling as a resistance, which I'll just be able to mention it to you that we are just calling it as an impedance. So first of all, let us look. Whenever we are having a resistor and a capacitor connected in a series, let's start with our first case. That whenever we are having, let's say, a resistor and a capacitor connected in a series. That I'm having a resistor there and a capacitor there connected in a series across an AC source. So this is a capacitor and this is a resistor. So we are having a voltage across a resistor and the voltage across a capacitor, through which you could be having the voltage across it. Remember, this is an AC source. So that, as you have already found previously, that the voltage and the current through a resistor, they are in phase. But for a capacitor, the voltage lags behind the current by 90 degrees. So the resultant could be shown by the use of what we call phasor diagram. So the phasor diagram, I could just be able to draw very quickly here, because we are just going to have just like rotating vectors. And if I'm having, let's say, this to be the voltage through a resistor and the current through a resistor, they are in phase, then the voltage through a capacitor lags behind. So it will be lags behind 90 degrees, so it will be moving like this. So to get the resultant, then we could just be able to use the Pythagoras theorem to get the resultant of the applied voltage V. So the resultant of the applied voltage V could just be obtained by the use of the Pythagoras, whereby V squared here will just be equal to voltage through a resistor squared plus the voltage through a capacitor squared. So to get the resultant voltage V, then we need just to take this particular expression, that is through R, this is just equal to I squared times R. Through the capacitor, as I've already said previously, through a capacitor, this will just be equal to I squared times the capacitive reactance squared. And if you derive, let me do it for you for this first case, you'll just be able to find that you could be able to take I outside, and inside there will just be equal to R squared plus that much squared. And if you take this squared, you'll be having this much. So the I can be taken outside, and we are going to have V over I, taking I outside, and inside there we're just going to remain with R squared. We're just going to remain with R squared plus the capacitive reactance, and the capacitive reactance is 1 over the capacitive reactance there is 1 over omega C squared. We're having that. And if you look at this V over I, now this V over I is just like a resistance. Now that is not, now we are not calling this to be a resistance because it's a mixture of with some reactance, and this we are calling this to be an impedance. So we abbreviate this by calling this to be Z, and this will just be equal to R squared into 1 over omega squared C squared, the square root of that. So this is the impedance, an oppositional force to a circuit containing a resistor and a capacitor whenever they are connected in a series. Having obtained the impedance Z, the applied voltage V should be acting to a certain angle. Let me call this angle as phi. And therefore we also need to know the angle at which this applied voltage is acting. And we can be able to obtain this by looking the tan of that particular angle phi, of which I'm just going to take it to be an opposite of adjacent. The opposite is the voltage through a capacitor, and the adjacent is the voltage through a resistor. And as we have already said that the voltage through a capacitor just be equal to I times the capacitive reactance through a resistor is just be equal to IR. So current will cancel, and the voltage, the capacitive reactance, this will just be equal to 1 over omega C. So we divide by R, and you will just be able to find that the tan theta and the tan phi here will just be equal to 1 over RC times omega. And therefore we can be able to determine phi, which will just be which will be taken as a tan inverse of that much, 1 over RC times omega. So you can just be able to obtain the angle at which the applied voltage V is acting. Okay, I've just done this just to remind you. I do hope that whenever we're coming to the second case or the third case, I do hope, having obtained this, then I do hope whenever we're coming to the second case, whenever a resistor and an inductor are connected in series, and the last case, whenever a resistor, a capacitor, and an inductor are connected in series, we'll be getting some total impedance across them, as well as the angle at which the applied voltage is just acting. Let me take you to that particular two cases very quickly without having such a longer derivation, just like for this first case, which I've just done, just to remind you what you did in a class. Let's go for the second case. Whenever we're talking about a resistor and an inductor in series, so here we are having a resistor and an inductor connected in series across an AC source. This inductor, this is a resistor. So we all know that the current through a resistor and the voltage are in phase, but the voltage through an inductor leads the current by pi over 2, that is a quarter of a second. And therefore, whenever we just draw, whenever we are having a current crossing through them, we are going to have the effective applied voltage. So we can just be able to obtain this using the phasor diagram. So the phasor diagram, if I can be able to draw it for you, you will just be able to find that we are just going to have this kind of a graph. That is, the voltage through a resistor is there, and this will be the direction of the current. But the voltage through an inductor leads the voltage through a resistor by 90 degrees, so that the applied voltage across the combination V is acting over there, and it is leading by this particular angle phi. So that if we go through, you go through the same derivation as we did for the first case, you will eventually be able to get the total impedance there, and the total impedance there will just be equal to, the total impedance will just be equal to R squared into L omega squared. This is for the total impedance whenever a resistor and an inductor are connected in series. And if we are looking, let's say, the tan of that particular angle phi, so here you will just be taking the voltage through an inductor over the voltage through a resistor, opposite of adjacent, and this for an inductor is just equal to I times inductive reactance, and this is just equal to I times R. So you'll just be able to find that this will just be equal to, for an inductive reactance, this is just be equal to omega L. Okay, this will just be equal to omega L over omega L over R. Okay, we'll just be getting an omega L over R, and you can be able to determine what will just be the angle theta. So theta will just be equal to the tan inverse of that much, omega L over omega L over R. So here you will be able to get the angle at which the applied voltage V acts. Here we're just going to get that particular angle. Okay, let's go to our last case. Whenever we are having all three, a resistor, a capacitor, and an inductor, to be connected in series, this will be our third case. So this is our third case. That is, we are going to have a resistor, capacitor, and the inductor are connected in series. Whenever they are connected in series, we are having a resistor, a capacitor, and an inductor connected in series across an AC source. So this is a resistor, a capacitor, and an inductor. So we're having the voltage across a resistor, voltage across a capacitor, as well as the voltage across an inductor. So we could be having the total current crossing through these three circuit elements. Now the effective, having known, or if you just remember that the current and the voltage through a resistor, they are all in phase, but the voltage through a capacitor lags behind the current by pi over 2 or 90 degrees, and the voltage through an inductor leads the current by pi over 2. Then you drawing a phasor diagram. The phasor diagram could just be drawn and could just be like this. That we are having the voltage through a resistor and the current are just in phase, but the voltage through a capacitor are taking to this particular direction, and the voltage through a capacitor leads the voltage through a resistor. The voltage through an inductor, leads the voltage through a resistor by 90 degrees. So this will be the voltage through an inductor. And for that case, you can be able to see that the voltage through an inductor and that through a capacitor, they are antiparallel. So generally, you can be able to find that the voltage through an inductor really dominates. And therefore, the actual resultant will be somewhere there, acting into this particular direction. So this could just be equal to the difference between the voltage through an inductor minus the voltage through a capacitor. So the resultant now can just be obtained by using the Pythagoras, so that we could be able to find that the resultant voltage V will be acting to that particular direction at a certain angle phi. And that can just be determined as well in the same process as we did for the other previous cases. Two previous cases. So you can be able to do this and be able to obtain the impedance. If you go through, you'll eventually be able to get the total impedance of the combination of these three circuit elements will just be equal to R squared, will just be equal to R squared into omega L minus 1 over omega C. The whole of this is squared, so we take the square root of that. So we're having something like that. Or simply could just be equal to R squared. If omega is 2, it is equal to 2 pi f. If I'm taking omega to be equal to 2 pi times the frequency, so here we'll be having 2 pi f times L minus 1 over 2 pi f times C. So the whole of this is squared. So we take the whole of that, the square root. This will be giving us the impedance. The impedance is already, as mentioned, is also measured in ohms. So this will be the impedance. And as well, we can just be able to get even the angle at which the applied voltage V across the combination do act. So the tan theta will be taking the opposite of adjacent. The opposite is the resultant of an inductive voltage through an inductor to the voltage through a capacitor over the voltage through a resistor. And this can just go on. The voltage through an inductor, this is equal to I times inductive reactance, I minus capacitive reactance. So the whole of this we divide by R. And if we divide here, we're having an inductive reactance minus capacitive reactance over R, and we can be able to simplify this. We can be able to simplify this and obtain the final expression. Okay, so that if you go about deriving this, you will end up find that this kind of an expression you are going to get to be equal to L C omega squared minus 1 over R C omega. So this will just be equal to tan theta. This will just be equal to tan phi. And phi will be equal to the inverse tan of that much, where that particular angle theta of the applied voltage can just be obtained. Okay, students, now having gone through these three cases, as I've already mentioned here, we can just go, I can just be able to take you very quickly to some model questions which might be helpful to you to see the way we can just be able to go about solving this kind of problems. Okay. Students, let's go to question number 1. The question goes like this. A group of students connected a capacitor of 20 microfarad and a resistor of 250 ohms in series to an AC supply of 220 volts and 50 hertz. Determine A, the voltage across the resistor and the capacitor, B, the current that flows in a circuit, and C, the impedance Z of the circuit. These are the three questions. The first case, the first one, part A, we need to look at the voltage across a resistor and a capacitor. So here we are having a resistor and a capacitor connected in series. So we are having a resistor there and a capacitor connected in series across that particular AC source. And we are given there, that is the capacitor is of 20 microfarad, that is 20 times 10 power minus 6 farad, and the resistor, that is 250 ohms, 250 ohms. And our AC source there, the supply voltage, an AC supply voltage, this is of 220 volts and 50 hertz. So we need to go to part A, the voltage across the resistor and the capacitor. The voltage across a resistor and the voltage across a capacitor. So first of all, the voltage across a resistor is just equal to IR. It's just equal to IR, and we could just be able to determine this. And we could just be able to determine this. And the voltage, this across the resistor. And the voltage through a capacitor, this will just be equal to I times capacitive reactance. So first of all, we need to obtain the actual current. To obtain the actual current flowing through the circuit, we need to know about the impedance. And whenever we are having a resistor and a capacitor connected in a series, the impedance Z, this is just equal to R squared, and will just be equal to R squared into 1 over omega C, the whole of this is squared, the square root of that. This will be giving us the total impedance, and we can be able to substitute to obtain the impedance there. The value for the resistance there is 250, we square, so we're going to take this to be equal to 2 pi F times C. This is 20 microfarad, that is we multiply times 20, 10 power minus 6, and we get the square root of that to obtain the total impedance. And we can just be able to obtain this by just computing very quickly to obtain this much. That this one here will be equal to 625 00, and this will just be equal to 1 over that much 2 times f, the frequencies of 50 hertz there, so it is 2 times 3.14 times 50 times 20 minus 6, so we are getting 6.28 times 10 power minus 3. Now remember, here we have to square this, so it means that we have to square this so that we could be able to take the square root of that. So let me just look straightforward the value for that, and will be equal to that. Now if I square straightforward, I'm going to get, this will be equal to 62,500 plus plus 355.99. So if I add with 62,500, I'm going to get that answer. Let me take the square root straightforward to get the answer. This will be equal to 296.4. 296.405. The impedance. So this will be in ohms. And therefore, if I go and look for, this will be the impedance, okay, for the whole circuit. To get the current, we all know that V from the Ohm's law, which is equal to V times IR. So the current I, now instead of R, it's just like the impedance. So that the current I will just be equal to the voltage we divide by the total impedance. So the total voltage that is 220. So the total voltage that is 220 we divide by the total impedance, which is 296.405, to get the current. And therefore I take this I'm getting the current to be equal to 0.7422. 0.7422 ampere. This is the current. If you could just be able to follow me, it was very difficult to start solving part A unless you solve part C. So actually, this was for part C, the impedance that flows, the impedance of the circuit, and part B, the current that is flowing in the circuit. So this much, and this will take us to solve the rest, to solve part A, to obtain the voltage across the resistor and through a capacitor. So that the voltage, as already mentioned here, the voltage through a resistor, the voltage through a resistor is equal to the current. Now that current is equal to this much, which is equal to 0.7422. We multiply with the resistance, which is 250. You'll be able to obtain. We need to find the voltage. Sorry, the voltage just be equal to current times the resistance. Okay, so we compute there to get the voltage, and if you multiply there times 250, you obtain 185.55. 185.55. This is the voltage across a resistor. This is the voltage across the resistor. Okay, let us look the voltage through a capacitor. The voltage through a capacitor will just be equal to the current times the capacitive reactance. This will be the current times 1 over 2 pi F times C. The current there is equal to 0.7422. Now we need to compute for the capacitive reactance. So we multiply 2 times 3.14 times 50 times 20 that much. I multiply. So here I'm getting 159.2356 multiplied by 0.7422. We are getting 118.1847. This is the volts. This is the voltage through an inductor, and this is for part A, and that will just be the end of question number 1. So let's go to question number 2. Here is the question. A student connected a 2 microfarad capacitance, 2 millihenry inductor, and 50 ohm resistor in series to an AC source of 50 volts and 10 power 4 hertz. That is 10,000 hertz. A. Determine the impedance of the circuit. B. What is the value of the current to be flowing in such a circuit? Okay, this question, if we could have followed me, it's just very easy. That here we are having a capacitor, an inductor, and a resistor connected in series. So we are having a capacitor, a resistor, and an inductor connected in series across an AC source. So you are having a capacitor, a resistor, and an inductor. And this AC source is of 50 hertz, it's of 50 volts and 10 power 4 hertz. And the capacitor there is given to be of 2 microfarad. This is equal to 2 times 10 power minus 6 farad. And a resistor is of 50 ohm. And an inductor L is of 3 millihenry. That is 3 times 10 power minus 3 henries. So we need to determine the impedance. The impedance of the circuit for part A. The impedance for the circuit, this will just be equal to R squared plus L omega into 1 minus C omega. The whole of this is squared. So we take the square root of that. And here we'll be getting the R squared plus 2 pi FL into 1 over 2 pi the omega C, 2 pi FC. So the whole of this is squared. So we need to determine the square root of the whole of that much. The R, that is the resistance, is of 50 ohms. And here is just equal to 2 pi F times L in an inductor, which is equal to 3 times 10 power minus 3 minus 1 over 2 pi times F. The frequency there is of 10 power 4 hertz. And we need to multiply with the capacitance C, which is 2 times 10 power negative 6, 2 microfarad, 2 times 10 power minus 6. And the whole of this much we square, and this is 50 squared, and finally we'll be able to determine the square root of this much. Now from there, this is just an arithmetic of which I believe you can be able to substitute and be able to get the total impedance, which will just be equal to 187.23 ohms. So this will just be for the part A, because what you can be able to do it here is just an arithmetic, of which I believe you can just be able to do it very comfortably by substituting and calculating, looking for the square root. Part B, what is the value of the current which will be flowing through the circuit? Now, having obtained the impedance, we all know that from the Ohm's law, V is equal to I times the impedance. So the current I will just be equal to the voltage divided by the impedance Z. Now the impedance have already been obtained here, and the voltage for the AC source is of 50 volts, and then you can just be able to calculate. That will be equal to 50 over 187.23. This will be giving you the value of the current in amperes, of which you can as well be able to calculate this. You are taking 50, you divide it to the total impedance, which is equal to 187.23. You'll be getting the current, which is equal to 0.267. 0.267 amperes. This is the current that is just flowing in that particular circuit. That's the end of the question number 2. Okay, students, now after having obtained done the second question, we'll just go for a short break, and when we come, I'll be able to share with you some 2 questions, take them as for homework. Okay, students, let's go for the homework question. This is question 1, and it goes like this. A capacitor of 3 microfarad and a resistor of 1000 ohms are connected in series in a circuit across an AC power supply of 12 volts, root mean square, and of 50 hertz. Find the current flowing through the circuit. B, find the voltage across the capacitor. C, find the phase angle between the applied EMF and the current. And D, the average power supplied. So this is the question. And we are given some 2 circuit elements, a capacitor and a resistor, which are connected in series across an AC power supply. So as long as we are together, you have just followed me from the very beginning, this question isn't difficult for you to do. That you are having a capacitor and a resistor. So a capacitor and a resistors, they are connected in series across an AC source, of 12 volts and 50 hertz. To find the current flowing through the circuit, first of all, you need to determine the total impedance of the circuit. And the total impedance the impedance of the circuit due to a capacitor and a resistor, this is just equal to R squared. Due to a capacitor and a resistor is equal to R squared, and this is just equal to 1 over C omega squared. You take the square root of that. Whenever you have obtained this, you can be able to get the current, where you'll be able to take the ratio of the voltage over the impedance. You can be able to get the current. That is for part A. As a hint, you can be able to do it. Having obtained this, you can be able to obtain the voltage across the capacitor. Remember, the voltage across a capacitor plus the voltage across the resistor is equal to the total voltage of the supply voltage. Supply voltage is of 12 volts. And I hope you can be able to do it for part B. The phase angle between the applied EMF and the current. Remember here, we are from the phasor diagram, that the current through the voltage lags behind the applied current and the voltage through a resistor. So the applied voltage, the resultant voltage, can just be obtained by taking the Pythagoras theorem. So this will be the applied voltage, and the angle at which it lags is that one there, of where you can just be able to calculate. So the phase angle can just be obtained in that way. And finally, you can be able to obtain the power for part D. Whenever you are looking for a power, the power is a product of the current I times the voltage V. Okay, so the average power applied, you can just be able to take the product of the current. Now the current through the circuit had been obtained from part A, and the voltage V is the supply voltage, which is 12 volts, That is 12 volts, the supply voltage here, which is 12 volts, and you can be able to calculate part D. Now that's just very easy, very simple. You can be able to do it. Okay, students, having done this particular question, I hope it will just be very easy for you now to embark to some other related questions of where we could be having a capacitor, a resistor, and an inductor connected in series. The various problems, and I hope you can just be able to find them to be much more easy for you to do it, as long as you understand the way the current and the voltage through a capacitor, inductor, or a resistor, which one leads the other or lags behind the other. Once you have just obtained that, then you could just be able to do those particular questions comfortably. Thank you, students, for listening, and see you next time.